We're going to look now a bit about energy and simple harmonic motion. And we talked about this a little bit in previous videos. So we're going to do this setup where we have a spring attached to a wall, attached to some block of mass m on a frictionless surface, and this spring is going to oscillate forwards and backwards. So simple harmonic motion. The amplitude or the position will change from some equilibrium position, x equals 0, to some maximum position, amplitude, and some negative amplitude as this thing oscillates back and forth. Now, in the pendulum example, the pendulum ball, as it's swaying back and forth, the pendulum ball rose up, went down, rose up. So what it was doing, it was exchanging gravitational potential energy for kinetic energy, back and forth, kind of like a roller coaster in the examples we did earlier this semester. Where a roller coaster, when it's high up, has a lot of gravitational potential energy. As it loses gravitational potential energy, it turns into kinetic energy, the roller coaster speeds up, and then as it comes back up the next hill, it slows again, exchanging kinetic energy back into gravitational potential energy. Now, assuming these forces are conservative, meaning that you can recover, right, the forces in both directions are the same, there's no energy lost to friction or drag, which are non-conservative forces, you can conserve mechanical energy. So kinetic energy, which if you remember the equation of which is 1/2 the mass of the object times the speed of the object squared, and potential energy, which is 1/2 the spring constant or elastic constant times the displacement from equilibrium squared, are the two energies involved in this spring example. So a pendulum deals with gravitational potential energy. Here, the mass is on the same plane, moving back and forth, back and forth, back and forth. So there's no change in gravitational potential energy, but there is change in spring potential energy. So, assuming no frictional forces, so the block as it slides on the platform isn't losing energy to friction, which in reality, of course, it would. Assuming no drag forces, that as the block pushes the air, as it moves through the air, that it's not losing energy because of that. Energy is conserved in this system, making those assumptions. So the kinetic energy, not the total kinetic energy, but the kinetic energy at any moment in time, plus the spring potential energy at any moment in time must be constant, right? So kinetic energy is turning into spring potential energy, which is turning back into kinetic energy, which is turning into spring potential energy as this thing oscillates back and forth. At any point in time, all of those energies have to equal some constant, some total energy of the system, like they did with our roller coaster examples a few units ago. At the maximum amplitude, when the block is extended its maximum amount, the position is the maximum amplitude, and the velocity at that position is 0. That's where the block turns around. So you have a block here, here's the spring sticking out. The block extends to some maximum distance, here's the equilibrium position, extends to some maximum distance, turns around, and comes back. So at that moment, when the block is going from some positive velocity to some negative velocity, its velocity at that instant is 0. So at its maximum amplitude, its maximum displacement, the speed is 0. Since at all times the kinetic energy plus the potential energy must be constant, the maximum energy has to be 1/2 k times the amplitude squared. Because when v is 0, this term is 0. So all of the energy is in the potential energy. So this must be the maximum energy of the system. So when you start this thing oscillating, the further you pull it back to get going, the bigger the amplitude you give it, the more energy you give it. More energy you give the system. So the kinetic energy at any point in time, plus the elastic potential energy at that same instant in time, must equal the total energy of the system, which is 1/2 k times the amplitude squared. So this is displacement, this is small x. This is amplitude, this is big X. Small x is changing with time as this thing oscillates back and forth. Big X is not. Big X is the maximum displacement, the amplitude. That stays constant with time, assuming there's no friction, assuming there's no drag. Now at the equilibrium position, when you're at x equals 0, the spring potential energy is 0. So all of the energy is in the kinetic energy. So the maximum energy, the velocity, has to be some maximum velocity. So this block is fastest at the equilibrium position as it passes through the equilibrium position. So all of the energy is in kinetic energy, which means the maximum energy must be 1/2 m times V max squared, where V max is the maximum kinetic energy. So if we know the total energy has to be this, 1/2 k times the maximum amplitude squared, and we know the total energy also has to be 1/2 m times the maximum velocity squared, we can set those equal to each other, as I've done here. Solve this, the 1/2 will cancel, rearrange to solve this for the maximum velocity, and you find that the maximum velocity of this system is equal to the square root of k over m, the spring constant over the mass, times the amplitude. So if you know the amplitude of the system, if you know the spring constant and you know the mass, you can actually figure out what the maximum velocity is of the system. So this is a discussion of the energy of the system. So what happens when there is friction? What happens when there is a drag force? What happens when energy is sapped from the system from these non-conservative forces? Well, we'll be talking about that in the next video when we deal with damped motion.